cross section or the thickness of the conductor affect the resistance of the conductor. Let's do activity 1. For this activity, we need a nichrome wire, a 10 watts bulb and a plug key, some connecting wires and ammeter which can measure up to 5 ampere range. Set up the circuit by connecting 4 dry cells of 1.5 each in series with the ammeter, leaving a gap XY in the circuit. Complete the circuit by connecting nichrome wire in the gap XY. Plug the key and complete the circuit so that the current flow in the circuit. Note down the ammeter reading. Take out the key from the plug and replace the nichrome wire with a torch bulb in the circuit. Plug the key and complete the circuit. Find the current through it by measuring the reading of the ammeter. Now replace the torch bulb with a 10 watts bulb in the circuit. Plug the key and complete the circuit and note down the ammeter reading. Now analyze the observation. In this activity, we observe that the current is different for different components. Why do they differ? Certain components offer easy path for the flow of electric current while others resist the flow. We know that the motion of electrons in an electric circuit consists of electric current. The electrons are not completely free to move within the conductor. They are restrained by the attraction of atom among which they move. Thus, the motion of electrons through a conductor is retarded by its resistance. From this activity, we can conclude that the resistance of a conductor depends on the nature of the material of the conductor. Depending on the nature of the material of the conductor, we can classify conductor as good conductor, resistor, a poor conductor, and an insulator. A component of a given size that offers a low resistance is called good conductor. A conductor having some appreciable resistance is called resistor. A component of identical size that offers a high resistance is a poor conductor. An insulator of same size offers even high resistance. Let's do activity 2. For this activity, we need a cell, an ammeter, a nichrome wire of length L and a plug key. Connect the circuit. Complete the circuit by connecting the nichrome wire of length L in the gap XY. Plug the key and complete the circuit so that the current flow in the circuit. Note down the ammeter reading. Take out the key from the plug. Replace the nichrome wire of length L with another nichrome wire of same thickness but twice the length, that is 2L. Plug the key and complete the circuit so that the current flow in the circuit. Note down the ammeter reading. Now replace the wire by a thicker nichrome wire of same length L. A thicker wire has a large cross-sectional area. Again, note down the current through the circuit. Instead of taking a nichrome wire, connect a copper wire in the circuit. Let the wire be of same length and same area of cross-section as that of first nichrome wire. Note the value of the current. We have the following observations. We have observed that the ammeter reading decreases to 1/2 when the wire of same material and of same length is used in the circuit. A change in ammeter reading is observed when a wire of different material of the same length and same cross-sectional area is used. On applying Ohm's law, resistance is a ratio of potential difference between the endpoints of the conductor to the current flowing through the conductor due to this potential difference. From Ohm's law, V by I is a constant called resistance for a given conductor. From the observation, the resistance of a conductor depends on first, on its length, second, on its area of cross-section, and third, on the nature of the material. The precise measurements have shown that the resistance of a uniform metallic conductor is directly proportional to its length and inversely proportional to the area of cross-section. Let the length is denoted by L, an area of cross-section is denoted by A, and the resistance R is given by R proportional to I. and also are inversely proportional to A, are proportional to L by A, or R is equal to rho L by A, where rho is a constant of proportionality and is called electrical resistivity of the material of the conductor. The SI unit of resistivity is ohm meter. It is a characteristic property of the material. The material and alloys have very low resistivity in the range of 10 raised to minus 18 ohm meter to 10 raised to minus 6 ohm meter. They are good conductors of electricity. Insulators like rubber, glass have a resistivity of the order of 10 raised to 12 to 10 raised to 17 ohm meter. Both the resistance and resistivity of a material varies with temperature. The table shows electrical resistivity of some substance at 20 degrees Celsius. You need not to memorize these values. You can use these values for solving numerical problems. The table reveals that the resistivity of an alloy is generally higher than that of its constituent materials. Alloys do not oxidize readily at high temperatures. For this reason, they are commonly used in electrical heating devices like electric iron, toasters, etc. Tungsten is used almost exclusively for filaments of electrical bulbs, whereas copper and aluminum are generally used for electrical transmission lines.